The monitoring of a precast pre-stressed girder bridge during fabrication and service provided the opportunity to observe temperature variations and to evaluate the accuracy of calculated strain and cambers. The use of high curing temperatures during the fabrication affects the level of pre-stress because the strand length is fixed during the heating, the coefficient of thermal expansion of steel and the concrete differ, and the concrete temperature distribution may not be uniform. For the girder discussed here, these effects combined to reduce the calculated pre-stressing stress from the original design values at release by 3 to 7%, to reduce the initial camber by 26 to 40%, and to increase the bottom tension stress in service by 12 to 27%. The main effect of applying the standard service temperature profiles to the bridge was to increase the bottom stress by 60% of the allowable tension stress. These effects can be compensated for by increasing the amount of pre-stressing steel, but to increase pre-stress losses requiring yet more strands and higher concrete strength requirements at release. Temperatures, strains, and cambers were measured in 5 girders in a pre-stressed concrete bridge and a matching test girder. These measurements were recorded during fabrication and for 3 years while the bridge was in service. The measurements were used to study stress and camber changes caused by the elevated curing temperatures and by variations in service temperatures. A method was developed for predicting the resulting variations in strains, stresses, and cambers. The accuracy of this method was then evaluated using field measurements of strain and cambers.
This manuscript studied the structural performances of bonded pre-stressed concrete beams at different load temperatures ranging from 20 degrees Celsius to 100 degrees Celsius. The main parameters of analysis and discussion were temperature and pre-stress levels. Theoretical models were proposed to predict the cracking and ultimate resistances of the bonded pre-stressed concrete beams at low temperatures. Numerical model was also proposed to stimulate behaviors of pre-stressed concrete beams at low temperatures. The accuracies of these theoretical and numerical models were validated against the test results. Compressive tests on concrete after freeze-thaw cycles were also carried out to obtain the corresponding mechanical properties. With these test results as input information, numerical parametric studies were performed to study the behaviors of bonded pre-stressed concrete beams at low temperatures or after freeze-thaw cycles. To summarize the whole study, these are the few highlights. The low temperature improves cracking and ultimate resistances of bonded pre-stressed concrete beams. Proposed theoretical models predict well resistances of bonded pre-stressed concrete beams at low temperatures. Proposed finite element method predict well behaviors of bonded pre-stressed concrete beams at low temperatures. Strength and elastic modules of concrete decrease after freeze-thaw cycles. And last, behaviors of pre-stressed concrete beams were changed by low temperatures and freeze-thaw cycles.
Precessing technique has been widely used in civilian and military constructions. Precessed reinforced concrete outperformed the non-precessed reinforced concrete components because of the following reasons. First, the increase in structural stiffness. Second, the load carrying capacity is also increased. And lastly, the high cracking resistance is also increased. Blast loadings are examples of loadings that a structure resists. These loadings are due to the terrorist attacks and gas explosion. Many studies were conducted regarding the blast loadings in reinforced concrete, but only few studies are regarding the pre-stressed beam. One study conducted by Wen-Su Chen et al. Entitled Numerical Analysis of Pre-stressed Reinforced Concrete Beam Subjected to Blast Loading, where it used final element codes such as LA-DYNA to numerically investigate the simply supported pre-stressed beam with rectangular sections subjected to blast loadings. Based on the test and results, the researchers concluded that the appearance and growth of flexural cracks in concrete is effectively delayed by using pre-stress. Also, the higher the pre-stress, the compressive strength, and the more effective the pre-stressed concrete to the blast-resistant capacity. However, increasing the pre-stress level in the beam may increase the diagonal shear damage near the beam supports and become a disadvantage in blast-resistant capacity. Therefore, proper analysis and design are necessary to determine optimal pre-stressing levels.
Pre-stressed concrete structures are an attractive alternative for long-span bridges and have been used worldwide since the 1950s. Savings in materials and maintenance and life cycle cost are additional advantages. The extensive application of pre-stressed concrete to buildings, military constructions, and civil infrastructure has been generally enhanced by awareness with its principles, practice, and further advances in its design. Although strengthening of structures by post-tensioning is much more common, in practice, the authors did locate innovative literature on the theory and applications of post-compression which form the basis of this study. One important technique of pre-stressing that has not received wide practical application is the use of slender compressed steel bars in concrete structures, which was first proposed in the early 1950s by Kurt Billig. So post-compressing structure is similar to post-tensioning in a structure except that the member is subjected to axial tension rather than the axial compression. So as you can see, this is the bridge. This is the first bridge made by the post-compressed bars in Bridge, Austria. So furthermore, a diagram is developed to show the feasible solution regions for different loading conditions. It is called the Magnell's method for the analysis of a pre-stressed concrete beam. It is very useful for the determination of safe pre-stressing. So in the analytical study of simple beam, the pre-stressing forces in the post-tension tendons are found to be independent of the eccentricity ratio. So the pre-stressing force ratio and the eccentricity ratio have direct effects on the eccentricities. So in the first figure, you can see the post-compression and post-tension tendon, and the other figure is the relationship of the eccentricity with the pre-stressing force ratio. So lastly, the findings revealed that the pre-stressing forces in the post-tension tendons are independent of the eccentricity ratio, but increases perfectly curved linearly up to a pre-stressing ratio of 0.7 beyond, which the technique becomes impracticable. On this basis, there is a realistic reduction of 50% in the eccentricity and possibly the overall depth of the concrete section over the conventional technique. This qualifies the structural innovation as a reliable candidate for long-span structures.
Pre-stress losses of double T girders cast with lightweight self-consolidating concrete. Pre-stress loss estimation is a necessary and important procedure in design of pre-tension concrete girders. The current specifications were developed from the experimental results of normal weight concrete that are possible inaccurate in estimating pre-stress losses for members cast with lightweight self-consolidating concrete or SCC. This study measures losses for two full-scale double T girders cast with sand lightweight SCC. Expanded clay, which had a specific gravity of 1.25 and an absorption capacity of 15%, was used as the lightweight coarse aggregate for the designed concrete mixture. The pre-stress losses were measured for 26 and at 83 days using vibrating wire strain gauges attached to the pre-stressing strands, after which the tested girders were then used in the construction of a parking garage. The experimental results indicated that the modulus of elasticity of lightweight SCC can be predicted using a correction factor of 0.99. The measured elastic shortening or loss was slightly lower than the predicted value. The predicted time-dependent losses, however, significantly overestimated the measured results, which yielded the overestimation of total pre-stress losses that varied from 86% to 153%.